It is one of the highlights of Alaska's Inside Passage. It covers over 13,000 square kilometers of rugged snow-capped mountains, glaciers, freshwater lakes, and deep fjords. This week we take a closer look at part of the Glacier Bay National Park and Preserve, along the coast of Southeast Alaska. Welcome to Earth from Space. The Glacier Bay National Park and Preserve, featured in this image captured by Copernicus Sentinel-2, contains some of the world's most impressive glaciers that descend from the ice-covered St. Elias Range in the east and the Fairweather Range in the west, with a few notable tidewater glaciers extending all the way to the sea. Johns Hopkins Glacier is the largest tidewater glacier in the region. Muir Glacier once rose around 80 meters above water and was nearly 3 kilometers wide, but has now shrunk and receded and no longer reaches the sea. Glacier Bay is just one of the many areas suffering from the effects of global warming. The bay is expected to become warmer and drier over the next century, with widespread effects including the further shrinking glaciers, reduced sea ice, and shoreline erosion. Monitoring glaciers is often a challenge, considering their sheer size, remoteness, and rugged terrain they occupy. Satellites including ESA's Cryosat mission, with its elite spaceborne sensor, the radar altimeter, allows for the mapping of glaciers in fine detail. In a study published last year in the Cryosphere, scientists utilized data from the Cryosat mission to show how much ice had been lost from mountain glaciers in the Gulf of Alaska. An exhibition opening today in Aosta Valley, Italy, offers its visitors the opportunity to witness the effects of global warming through the power of both photography and ESA satellite imagery. The exhibition focuses on the world's largest mountain glaciers with 90 photographic comparisons displayed alongside scientific data, and includes images such as the one featured in this week's edition.
Coming up on the opening.
Well, hello everybody. This is Scott Roberts and Dr. Daniel Barth, and it's our 51st episode of How Do You Know? And this particular episode is going to be all about your questions, your science questions, your space science and astronomy questions. And so I'll let you roll it out here, Daniel, and we'll see what kind of questions we get from our audience.
Thank you.
And
thank you, Scott.
and I'm sure I'll have a couple of curveballs for you as well.
That'd be great. 50 episodes is awesome. We're also going to be
giving away some books today. So we're looking for 3 best questions. Scott and I will be judging that. So make sure
Okay.
when you post questions on the chat or send them in by email, you give us your information so we can contact you. Okay, email or Facebook handle or whatever. So if you're a winner today, we want to be able to give you a book. We want to contact you, and we'll ask you how you would like it signed. And I'm still waiting for my author copies, which is just silly. This is like 6 weeks ago. We decided we would give away some books. I said, I'll have them by then. Anyway, but as soon as we get them, you guys will have them. And so that's exciting. So we hope you'll be contributing with questions today. So it's what we used to say during exam review time in my classroom. It's time to ask Doc anything.
Right.
So I'm hoping we will get some interesting questions. I'm hoping we will stick primarily to science-oriented and math-oriented topics, that
Right.
sort of thing.
Yeah.
You
Maybe
know, the
not
farther you
like
get away from
how about
my
meaning of life questions? Is that allowed
yeah,
or
the
not?
farther you get away from my core expertise, the shakier the whole thing gets.
I also want to mention that it looks like that there's some news today about fires reaching Kitt Peak National Observatory. So
Oh, I know.
yeah,
Oh,
apparently they've lost some non-scientific buildings, but it's getting close to the telescopes. And
horrible.
so anyhow, we're hoping that things are turning out okay for those guys up there.
Yeah, that's a terrible situation for them.
Sure.
And I don't know what it would be like to have big quantities of the fire retardant junk dropped around the telescopes and the optical instruments.
Right.
But I'm sure they'd be happy with no fire.
Yeah, absolutely. So have you been to Kitt Peak before?
I have not been to Kitt Peak. I've been to Palomar. I've been to Mount Wilson. I've been out in the deep Mojave. I've been down on Indian reservation land in Inyo County, which was maybe I've got the county wrong. It was basically in the desert east of San Diego, Imperial County, maybe. Anyway, but I got to go out observing there one night where Jupiter was bright enough to cast a shadow on the ground. It was quite astounding. So you talk about highly transparent skies, and this would have been, I don't know, sometime early 90s, mid 90s, something like that. So that was exciting and fun. And yeah, we've been doing lots of work on the house, painting and maintenance and all sorts of crazy stuff.
Sure.
Seems like summer, all the projects just go and they just kind of pop like popcorn, and your weeks get eaten up.
I will start with a simple question for you because tomorrow will be the day of the solstice. Okay. And so, for us, it's the summer solstice, it's the winter solstice in the southern hemisphere.
Right.
How much do we know? I mean, they give like a specific time that it's going to happen and everything. How is all that stuff calculated?
When we're talking about solstice, we're talking about that point when the sun is, I believe it is at noon on the longest day, and basically the sun has to occupy a certain position in space, viewed from Earth, of course, and that alignment when the Earth and sun and moon are aligned precisely, and we think about it and we say, well, we got the longest day of the year. That means the line of our axis, as it's tipped away, it swings around in orbit, and that one point is directly pointed at the sun, and it occurs at a particular instant. So the
Right.
solstice is a precise alignment with the Earth and its axis and the sun, and
So
it
for
got a.
here
There's a number of ways.
here in Arkansas, we're in Central
Yeah,
Time Zone. So at the Central Time Zone, it's going to happen at 4:13 a.m. I'm sure it's going to
right,
happen at noon somewhere on planet Earth, but
right.
I'm sure that there is, the people that figure this stuff out. It would be interesting to know more of that backstory.
Yeah, and I'm imagining a lot of that stuff has to do with when they set up the line through Greenwich as being the 0 point, right?
I
The
see.
British were in control of things at the time. And so they set that up. And when they set that up, and you realize that the zero meridian on any planet is an arbitrary choice. It's not like a North Pole or a South Polar axis where it's an axis of rotation and you can pinpoint it geographically and it's here for these certain reasons. The zero meridian is just a reference point that somebody says, yeah, this is zero right here, and everything around here goes either east or west. So those are arbitrary, which is kind of fun. So
So there's,
yes,
go ahead.
yep. And the latest sunset of the year follows the solstice by 3 to 4 days every year. And I believe our latest
Oh. Mm-hmm.
the latest sunset occurs, I think, on the 27th this year, 26th or 7th. And it's a two, like the solstice. It's a precise thing. And at this time of year, the sun goes down at the same minute. It's like 8:38 here. Goes down at the same minute for about 10 or 12 days because that sunset time is changing very slowly right now. And we're at an inflection point where we go from gaining daylight every day to losing it. And so, oddly, on that day when we toggle over to losing daylight every day, that's the summer season. Uh, and then autumn comes in the fall of the year from September to December, and then winter from
Right.
January or from December 21st through to March. What is it? And so it goes basically every 3 months. So yes, we're entering what we would call the waning time of the year because we'll get starting tomorrow. We'll get the most sunlight we get for wherever we are
Mm-hmm.
on Earth, and
So,
then
Dr. Barth,
after that, we start losing daylight until next December. But of course,
Okay.
the amount of solar energy we get in, the weather actually lags behind. There's a lag in there because we'll continue to get hotter weather now for the next 60 to 90 days. We expect
Okay.
here very warm weather that time of year, and then it'll
So
start to cool off.
one of the things I think about for the solstice is Stonehenge, right? I mean,
Yes,
and so there's articles.
yeah,
I'm reading one right now, and they say that before the pandemic, that about 30,000 people would show up at Stonehenge to watch the sunrise between the stones
right.
for the longest day of the year. Uh, and so it said pagans and some non-believers celebrate the event each year at Stonehenge.
Mhm.
When they say non-believers, they don't believe it's going to be the solstice, or is it a religious connotation? Maybe that's what it is. I
yeah,
don't
it's a religious holiday for the pagan community, and they're
know. Okay,
holding
all right.
census, if you
Okay.
will. And but they're
So,
basically most of those things are anybody all y'all come, as we would say in Arkansas.
so
Right?
right. Here's the
Dr.
bus
Barth
schedule.
and Scott,
They have a. I'm sorry.
we have a question from
Oh, you
Karim
do. Okay.
Jafar.
Okay.
All right. Well, let's
Says,
see.
hi, Dr.
We've
Barth.
recently.
A question
go
from
ahead.
one of my students. We've seen recently we can imagine the surface of a neutron star and see the points where the magnetic field is particularly strong. Is this like seeing sunspots? Have we been able to imagine the surface of a white dwarf? If not, why not?
Hi, Kareem. Yeah, the what you're really talking about when we say we can imagine that, what we're looking at there is a mathematical model. Scientists, mathematicians, astronomers have put data into a mathematical model and crunch that data and give us a visual picture. Here's what the surface of this star looks like. And how good is that image? It's as good as our understanding of the physics of these things are. And these neutron stars, where you're talking 100 billion tons in a teaspoon, something crazy like that. It's incredibly dense. We don't understand the physics of these sorts of bodies terribly well. It's so far beyond anything we can create here in a laboratory. The highest pressures we can create, two diamond anvils and compressing things, that's far, far less than what we get on the surface of a neutron star. The gravitational field is unbelievable, and if they're magnetars, then they're even more dangerous than that. So I'm hoping that's helpful for you. These are good questions. Who has some more, friends? We'd like to hear from some other people.
Now, the question I have is it the 50th or the 51st?
It's the 51st.
Uh-oh.
No, it's 51st. Am I wrong?
I think so, but I'm checking now.
Let me double check. The calendar says 51st, but that there may be an error
And
there.
I believe you. But the last one I have is episode number 49, the Hubble Constant
49,
History.
so 50. Okay,
So
so,
this
we
is
will
50.
we'll have to correct that posting and just make this the 50th one. So
all right.
that's it.
Yes, it's the 50th
All
episode.
right, that's
we
fine.
thought we would have we thought we would have books by now episode.
Right.
And we have an image of the book cover.
Oh, yeah.
And I just sent it to Paul a while ago so we can put it up. So we can see the.
So busy doing the other stuff. I apologize. Here we go.
It's okay.
All right, here we are.
So I want to make sure I've got chat on here. Here we go.
Nice.
There we go. So that's the book we're giving away for 3 best questions today, friends. So we're hoping we can have. We have people that ask me questions off the air and after the show every week. So where are you all, you guys? Come on. You got to be tossing in your questions.
Question here. We got one.
So Pekka, let's see. Pekka says, question, what force defines what kind of star a supernova ends to, whether it's a magnetar or a neutron star?
That's an excellent question. If you're going to become a magnetar, you have to be in a certain temperature range to where you can have convection of columns of hot material. And we're talking super collapsed neutrons. And it's hot enough that this material, 100, something like 100 million tons per teaspoon, crazy density, gets hot enough it can flow, can have convection currents. When it has convection currents, it sets up a dynamo and you get a magnetic field. And magnetic fields from neutron stars are the most powerful magnetic fields known in the universe, and they're kind of insane. Magnetars are. But what determines the final fate of a star when the supernova happens is the internal pressure. These objects, the neutron stars, resist compacting further because they have what they call degeneracy pressure. It's high enough pressure environment in the core that all the protons and electrons have been forced together to make neutrons, and there's no more positive or negative material there at all. But those things have a quantum degeneracy pressure. Without going too far into that, they can't occupy the same space at the same time. So it's just like having a fistful of marbles, and you can squeeze it very hard, but you can't get the marbles to squeeze into one another. If the pressure gets too high, it overwhelms degeneracy pressure, then it collapses all the way to a black hole. And exactly what side that tips on the final outcome during a supernova, we really don't understand the physics of that terrifically well at this point. There are theories, people argue, and they will present, but data to support one of these theories, or an experiment that would show this is right, that's wrong. I haven't evidence of yet, so we kind of have this. We think this is a pretty good model, and we run it for what it's worth, but we all understand that it's not going to be right on because we don't understand all the physics of what's going on there. Hoping that's helpful.
Mm-hmm. How about this question?
Sure.
Kind of jumping around a little bit. When I was at Caltech, Stephen Hawking gave a presentation, and he lamented that he had not won the Nobel Prize for Hawking radiation from a black hole. What is Hawking?
Were you at this personally?
Yes.
Yeah, I think I'm sure we were at the same place because he only came to Caltech on a couple of very memorable occasions.
Okay. All right. So Kip Thorne introduced him there.
Yes.
So we were probably both at the same. So you remember him talking about that, and he was making he was making all these jokes and stuff like that, but he kept coming back to, well, I hope that they give me a Nobel Prize for Hawking radiation, So what is the supposed Hawking radiation from a black hole?
Okay. Black holes are effectively very, very cold because all motion has been stopped. They're essentially supercooled. And at the very surface, you sometimes get the creation of virtual particles where you will have out of nothing, out of the vacuum, you will have a proton and an antiproton, right? Come into existence, they will travel for a little while, and then boop, they will disappear again. Near the edge of a black hole, what you can have is those two are created, and the lower one is captured in the black hole, and the upper one has just enough energy to escape. They're created right at the event horizon. Well, if a particle escapes, even a virtual particle carries mass away with it. And so E equals mc squared, it takes a lot of very lightweight photons to carry away mass, but it will happen eventually. And the black hole will evaporate, and as it shrinks, the rate of evaporation increases. Okay. And the last few seconds are quite violent, and it ends with a substantive bang. No one's ever seen this happen. There were some questions, maybe cosmic ray bursts are black holes evaporating, but no. There's the thought that some very tiny black holes should have been created in the Big Bang. They should still be wandering around. They should be nearing the end of their life. We should be able to look out and see them go pop. We have found experimental proof for Hawking type radiation, and we think this is a real thing. We think this works. And he probably should have gotten a Nobel Prize for it. But the Nobel Committee is not very good with that sort of thing. You need to discover something young and then live long enough for the Nobel Committee to figure it out.
To vet that this is a real deal. I see.
Yeah.
Wow. Okay. So, well, thank you. Mike Wiesner, watching on YouTube, asks, or he states, some people can see the thin crescent phase of Venus with the naked eye. How did ancient astronomers miss this imperfection and the implications of a phase of Venus?
You know, Mike, I've often thought of this, and the best idea I can come up with, I think what happened is people who have vision that's that good are the youngest and the most junior people on staff. The old and venerable guys with the blurry and squinting eyes, they're the ones whose opinion is taken absolutely. And if the master says, and Venus appears as a fuzzy dot, and you can actually see a crescent, are you going to say, no, master, you're wrong? I see a crescent. That would have gotten you nothing but a whooping and go to bed without supper. I think really because excellent vision resides mostly in the young, in a society that very much venerates the master and what the master says is true because they're the master and you're not, and that's sort of a societal milieu. It's very kind of authority-based, right? We believe what the authority says, not necessarily even the evidence of our own eyes. The cardinal who looked through Galileo's telescope and said, I see it, but I do not believe it. And so, we had people who could see it, but they weren't listened to. If you were, how old are you before you lose that very best vision of your life that you have, maybe starting when you're 16, and then you carry it with you until you're 25, 26, 28, maybe some rare individuals 30, but in this sort of a cultural thing, the masters are people who are usually 50 years old and been doing it for 30 years, and that's where their credentials are. So, and by that time, 30 years of squinting over parchment, how's your vision going to be? Not so good.
Okay. Let's see.
It's one of the miracles of Galileo's telescope because it democratizes good vision. Everyone can step up to a reflector or a refractor and adjust the focus for themselves and get the best image their eye can deliver to the brain. So it doesn't matter that you're young or old. That's what the great democratic sort of everybody gets a chance. The telescope gives everybody this superb vision.
Okay. How about, let's see. We have another question. Pekka's got a question. In magnetars, the neutrons can't be pressed as near to each other like in a neutron star. Can that have something with magnetic flow around the neutrons upward to build up the magnetic field?
The problem with atoms in a neutron star magnetic field, we're talking a magnetic billions of times stronger than the Earth's magnetic field. It's so strong that within about 1,000 kilometers, exposure to that kind of magnetism would be lethal. What happens, your atoms in your body have positive and negative parts. And in a relatively weak magnetic field, like let's say a very strong speaker magnet or a strong
Okay.
electromagnet, something like even an MRI, you know what? Your body, it isn't hurting you a bit. But this kind of magnetic field is so strong that the atoms essentially, instead of being spherical, now they're stretched out to where they're 100 or more times longer in one dimension, running along the lines of magnetic force. And so when atoms are distorted that way, they can't maintain bonds that hold together molecules like water, proteins, DNA, RNA, cellulose, sugars, heme, all these things, they just fall apart in this intense magnetic field. And so a magnetar, which has to be just hot enough, it can't be too hot because then everything super rotates and the coupling that's necessary to get the super strong magnetic field breaks down. So you have to look at these magnetars are tremendous, but literally nothing survives around them. Within a couple of thousand kilometers, matter just literally falls apart. Molecules just fall apart, and it's just a big stinking magnet. It's seriously crazy. And I'll have. I was going to do a show next week on magnetar, so we can talk about some of these things in more detail.
Right.
So, with the increase in commercial investment in space travel, what do you think will be the tipping point for governments to completely use the private sector? Well, I don't think that it's ever going to be 100% because there are always activities that governments want to do in space they would like to keep private and secret. And so there's always going
Right.
to be some portion of exploration and satellite deployment, which is going to be purely government, and they're not going to. God, I hope they don't. Oh, let's just let a random tech firm do this processing for us. No, please. We would prefer that secrets are kept secret. Um, anyway, but there you go. These are all good questions. Who has another one?
I've got one.
Sure.
If the universe has been expanding for 13.8 billion years, we know that things are out further than that because they are expanding. They've been still expanding out past what we can observe them. Is it postulated that if you could somehow keep going out in your magic spacecraft, do we run into an edge of the universe ever?
No. And part of it, you're bringing up a bit of misinformation that is quite common. The idea
Okay.
that, oh, we're expanding into something, and as we expand farther, we're going to now start. It's like we're getting close enough now that we can see the distant object. What's happening is space-time is expanding. Into what is not really clear. If into anything, we may just be seeing the universe, the entire fabric, all of it is expanding. So expanding into isn't really a question that makes any sense mathematically. Although it's very compelling philosophically. We are a bubble expanding in an ocean. We must be expanding into a volume. But no, in this case, the entire ocean is expanding with us. And when you talk about when we get farther out, when we look farther out in space, we're actually looking backward in time. We're looking back toward a period when the universe was more homogeneous and isotropic. We take it for granted today. The assumption is that the universe is both homogeneous and isotropic, the same everywhere we look, the same everywhere in terms of composition, throughout its volume. So we say that the universe is finite but not bounded. And how does that make any sense? Well,
Right.
you can think of an ant crawling over the surface of an apple. And at some point, the curvature is positive, and at some point, the curvature is negative towards the stem and areas like this. And the ant is crawling over and seeing these different curvatures and wondering, when do I come to the edge? Where's the boundary? And of course, on the surface, if the surface is the universe, there is no boundary. If it's a balloon we're crawling over as an ant, well, we can expand or contract the balloon, add more material inside it, or take it away. And so we can expand or contract the universe. But if you're on that surface, if that surface is your universe, then your universe is finite, but it does not have a boundary. And we can do this trick instead of just a 2D surface expanding into 3D space. We can do a 3D, 4D space. And the math works, the logic works, the physics works, until we get to things that are very highly compressed, very dense, or extremely high magnetic fields, or extremely great velocities. So,
Dr.
approaching
Barth,
infinite. Yes.
we've talked about this in brief about a month or so ago,
Okay.
but
Sure.
what was his name? Sir Roger Penrose, a
Okay.
mathematical physicist.
Yes, he's
He's
very smart
liking,
fellow.
he's liking the theory that once it all expands far enough, it's going to reverse course and contract back into a giant ball of matter. And I'm
The great
being
punch.
a really, really non-science understanding about this.
Okay.
So just kind of your thoughts. I was curious what you thought about it.
This is sometimes known as the circular universe. The universe expands for a while, bang, and then it reaches a tipping point and it falls back together with a crunch. Bang, crunch, bang, crunch, bang, crunch. We're talking balls of time. Anything that would make our 13.8 billion year experiment so far seem paltry and insignificant. So we're talking huge spans of time. I will tell you that when Dr. Penrose says the math is interesting, that this is possible, I tend to be a believer because his mind is indeed powerful and far-seeing. But you're going to say, oh, are there any experiments supporting this? No. This is a purely theoretical idea. The ideas of, it's come down to how does the universe end? The heat death, everything expands forever. It gets occupies bigger and bigger volume, which means the fixed amount of energy, everything gets colder and colder, and you end with what we call heat death of the universe. Everything is at lowest possible entropy, lowest possible temperature. And then there's the idea that the universe is expanding now, but it doesn't always expand, that it may accelerate and decelerate, and the size and direction of the universe, overall motion, may simply oscillate in time. We don't have a big enough data set to answer these sorts of. We just don't.
Thank you.
And these kind of things come out of sophisticated mathematical analysis of the sophisticated mathematical analysis of the data sets that come out of things like the Gaia Space Telescope and things that will come out of Webb and Webb's data set and Hubble's data set. And we've said it before, scientists, both citizen scientists, independent folk, and professional scientists at universities and institutes, they're all going over, there are people today going over Voyager data from the 70s, Viking data, Pioneer data, the Voyager spacecraft data sets, all the Martian rover and lander and orbiter spacecraft data sets. Most all of these are public domain because government space agencies put them in public domain. And there's tremendous amount of interest in these data sets. But the mathematics that will say, aha, I have discovered a new particle from the background data of the Voyager spacecraft or the SOHO solar observer, and I found this showing this new particle. People are going to be skeptical, and you're going to have to be able to show and hopefully reproduce your results with a bigger data set. So there you go. Does the particle-antiparticle happening from vacuum energy have any impact on the universe as a whole? And then a question about dark matter, why or why not? Does it have any impact on the energy as a whole? No. When these two particles come out of the vacuum energy and you get a positive and then a negative particle and they're essentially identical, and then they recombine and they release energy in a flash of gamma rays. And however much energy it took to create them, that's exactly how much is released. And the ledger is balanced. Now, when you have one of these crazy things near the event horizon of a black hole, and two particles are created and one falls in and the other escapes, then you have a situation where, the black hole owes the universe some energy or equivalent mass, E equals mc squared and all of that. And it turns out for a vacuum particle, you're emitting a proton, an electron, or a gamma ray. Goodness, that's not very much mass. But when you continue to lose anything over a sufficiently long period of time, it doesn't matter that the rate is tiny, because eventually is a long time from now. And these processes continue relentlessly. Could it account for dark matter? I doubt it, because the Hawking radiation particles are particles that we know of already and we can measure, and most of the time you're talking about charged particles, ions, and we know what those are and we know how they behave and react. There's nothing there that's showing off any unique physics once the particles themselves are created, come into being. After that, we pretty much understand how it works. How exactly two particles are created out of nothing and then recombine and disappear, we think we understand how they recombine and disappear. How they're created in the first place, golly, that's a wonderful mystery. We don't know that.
Here's another one for you from Pekka.
Mm-hmm.
Has there been done a survey on how many objects in space are on their real places and not behind a gravity force from view from the Earth? How we would view it from the Earth, I guess.
Pekka, are we talking about things like Einstein rings where we're looking at gravitational lensing? Is that what we're talking about here?
That would make sense to me.
Yeah, it looks like we're talking about gravitational lensing. one of the interesting things about gravitational lensing, it provides us with the opportunity to see an object like a star or a planet much farther away than we can otherwise possibly come close to seeing it. The bad part is that because there's a large mass, a big star, or even a small galaxy, right? It's in between us and that object, where we can't ever really see the object. The fact that there's something in the way that's gravitationally lensing everything, that would protect us or prevent us from seeing the original object. The only way we can see them is through these Einsteinian arcs and circles, um, and we're seeing these gravitational lens events, which are really fascinating. They're really exciting, but it's kind of odd because you're placing the magnifying object in between you and the camera, and the idea that the information has to be bent around it. It's a very fascinating idea. How far would we need to see something fade beyond the cosmic horizon? Well, again, that's kind of what's outside of everything. And the answer is it isn't. Your question, Josh, implies that there's some kind of boundary edge that can see beyond or expand fast enough that we finally move beyond. But that idea of an outer boundary is flawed. There's no real outer boundary like that. We're not expanding into anything. It's just the entire universe's fabric which is expanding. So, sorry on that one. Could space acceleration be a sign that gravitational constant is actually not constant and is weakening? This from Lubo. This is really fascinating, and there is a theory called MOND, MOND, which stands for Modified Newtonian Gravitational Dynamics. MOND says basically what we see as fluctuations in data in very old data sets. This is actually what we're seeing is in that epoch, G was different. The acceleration of gravity was different. The atomic forces were different, and these things were not constant over time. Now, we're not talking about decadal survey or human lifetime or the lifetime of a civilization. We're now talking cosmic time, billions of years, and we don't have the technology. Even if we could start today, an observing program that would go on for decades is really exceptional. Survey going on for more than a century is almost unheard of, and thousands of years we just haven't had the opportunity as a species. We're not that old yet. So hopefully we'll get to a point where we have that kind of long data sets. And I would hope that if you get enough data, you start to see patterns and things emerge from the data. It's really quite fascinating when it happens. There's no feeling like it. Okay. But time and light's path. Actually, it does. So some object can look like, okay. I'm reading a book right now called No Shadow of a Doubt by a colleague of mine, Dan Kennefick. And it's about the eclipse in 1919 and bringing evidentiary data to support relativity theory for the very first time. And in fact, the gravitation of our star was enough to bend and distort the position of the stars. The change was very, very small. And not unlike the detection of parallax. You're looking at a situation and saying, oh, well, gee, um, this happens over with very, very big masses. Our sun is barely enough to wrinkle the fabric. So the change is really, really small. And there were a lot of technical and mechanical challenges. The book No Shadow of a Doubt by Kennefic is highly recommended here. So, and anybody can read that and enjoy it. He's a very readable fellow. When we see something through a gravitational lens, can we know the direction and or distance of the actual object? Is it safe to assume a spherical lens and figure it out from that? We can know the actual distance because the size and shape of the rings tells us the shape of the cone. You have an object emitting something over here, and then over here, well, we have the receiving area. And so the light goes out and is refracted and brought back into focus. Well, yes, the geometry of those circles gives us the distance quite precisely. And when we get that distance, at that point, if we know what the object is, there's talk of what's a standard candle. If you know absolutely how far away something is, and number two, you know absolutely how much energy it's giving out, its luminosity, then you can use its brightness to compare distance one way, and you can use this geometry of the Einsteinian rings to give distance the other way, and hopefully the two methodologies, two completely independent calculations, will come together and give you one answer within a reasonable amount of error. So yes, we can get quite precise with measurements like these. Is there going to be a wide field survey map out differences in expansion rates in different parts of the sky? The Gaia survey that's going on right now is a deep sky survey that's covering much of the sky. And Gaia is releasing data. They release data, I don't know, is it annually or is it more often than that? But you can go and find the raw data if you want it. You need a lot of hard drive space because it's a lot of data. But yes, you could do that and you can study the raw data. And many people do. So the Gaia survey, there's a Hubble survey, there's a Hipparcos survey. And as I remember, Hubble was 10 million stars. Hipparcos was about 10 times that, I think. I'm shooting from the hip here now, folks. And Gaia is supposed to be the most impressive of the bunch. And it's designed to be a wide field survey instrument. So we'll see. Part of the idea of Gaia data is that it allows you to see changes in position of stars that are close enough. So we're measuring actual real motion, which is important for us for how our section of space is changing. Keep in mind that if we want to understand things at great distances relatively well, we have to understand what's close to us extremely well. Eventually, a sufficiently distant object will have stretched farther in space that light from it after a certain time will never reach us. Is that not something we could theoretically observe? Okay, do you have to be traveling the speed of light to do this? No, because the universe is expanding and contributes something to that speed. So yes, you can be moving at a speed which is great enough, a distance which is great enough that we on Earth will never be aware of you. If you are moving with your speed plus the expansion of space-time, you could be moving away faster than the expansion of the universe will reveal you. And so, yes, you can be forever hidden. but that means that you cannot discover us either. There's what's called a light cone or a cone of discovery, where the cone of discovery, this is our cone of information. Anything inside that cone will eventually make its way to us as light energy, and we can potentially capture it in a telescope, refract it in a spectrometer, get all sorts of data and information out of it, out of those photons, and extract information out of them. Terrific. But if you're too far away or moving too fast, that information will never reach us. It's like being beyond the event horizon of a black hole. When we see something in a gravitational lens, do we presume it is behind the object? Yes, that's the only way it works, is the object in between, and the light is spreading out, but the intense gravitational field corrects it, and it now travels. It's exactly the way a lens, a focusing lens, like a magnifying glass, refracts light and focuses it into a point. I'm assuming most of us have done a magnifying glass and burn a hole in a leaf sort of experiment, where we're basically bending the rays of the sun to focus at a particular point. This can happen on cosmic scales with very large objects such as black holes or supermassive black holes or galaxies. And you're actually talking, here's something in a distant galaxy far, far away, and here's a galaxy in between us, and here's Earth where we're looking, and that great mass of the galaxy acts as a gravitational lens, bends the fabric of space-time, refocuses the light, and so we get a chance to see something that is far too far away for our conventional instruments. So gravitational lensing is very, very cool.
Connor Bradley is asking, he says, do you believe there is a big discovery about the universe that we're close to discovering?
There is a what, please?
Is there a big discovery? Okay, like a major, huge discovery that we're getting close to discovering. Do you believe that there is like an earth-shattering, mind-bending, mind-melting discovery that
there's a couple discoveries that would change everything. So in a sense, yes. We've talked about the idea of life on Mars before. If Mars ever had life, could changes in climate ever completely sterilize the planet? I don't believe so. So there's the possibility we keep sending robots to kind of look for traces of ancient life on Mars, and we're looking for traces of ancient fossilized or extinct life, but nobody's looking for living things right now. I think that will probably require boots on the ground, people on the ground on Mars. But at that point, digging into the soil, taking the ice, testing, looking, seeing if we have active biota there. And that's something, the idea that life was found elsewhere than Earth, that would be this changes everything sort of a discovery. The other thing that I think we're close to, I hope to see it in my lifetime, not just boots on Mars, but permanent human habitation beyond the surface of the Earth. I have written about this as colonies floating at L points. I've written about this for colonies, city-sized colonies on the moon and on Mars in my fiction. And this is something, the idea that people are no longer confined to one planet. Gives us a little perspective, a little distance, and eventually these people living in colonies on Mars will no longer be from Milwaukee or Madagascar. They will simply be Martians who are from Mars. And humanity will be a multi-planet civilization. Question: have any Magnetar collisions registered? I don't think so. We don't know about very many Magnetars to begin with. It's a fairly low number. And collisions that we see when we detect them, when we're looking for LIGO data and we're looking for gravitational wave detection, uh, this is often neutron star collisions, or it's neutron star black hole or black hole black hole. When we're talking about things like this, the difference in mass between a small black hole and a neutron star is really very, very small. It's kind of the straw that breaks the camel's back, and bang, everything crushes down into a black hole. So when you say, oh, black hole and neutron star, the difference must be very large, but actually it's not. It can be a fairly fine outcome as to which way the stellar core goes after the big supernova explosion. So there we are.
All right, so we've got a couple of kind of out there questions right now. Charity Rose Walker is asking, who do you think would, if we have colonies on Mars, who would govern them? Is that already decided now?
Yes, no, it's not. I think the first prediction, true, just prediction, and I'm really putting on my science fiction author hat versus my astronomer hat. I believe the first successful colonies will be corporate rather than governmentally sponsored. So some corporate, Mitsubishi Heavy Industries, right? They're in everything from rockets to electric cars to chemistry to products. And they decide there it's advantageous for them financially to put a colony there for resources. And once that happens, the government will be local. You can't govern. You can't, if it's not a military installation where everybody's already sworn allegiance to a command structure, you're not going to be able to control a colony from 50 million miles away. When conversation back and forth has a 10-minute time lag, you have to be prepared. We found that with our robots. You have to give the rovers self-driving capability. Otherwise, it's intolerably slow. The thing has to be able to read out and find dangers and maneuver around them and call for help when it needs it. But the rovers have this ability. Sure, they do. Colonies are going to face the same problem. If you've got a 10-minute out, 10-minute back time delay, that's 20 minutes. You can already be over the cliff by then. So the people who live there and work there will govern themselves. I don't suspect they will always govern well, and they may have social experiments which are successful and some may be disastrous. Certainly, the last time we saw that was in an era of colonization on Earth between 1450 and 1800, where colonies would be sent to places and they would land and let's burn our boats and stay here, kind of Plymouth Rock or bust sort of mentality. And so we have this kind of situation. I think we'll have that situation again. I think when you think of heavy industry, the ability to make heavy machinery relies on steel and the ability to have that much energy available. As you move farther out in the solar system, heavy metals like iron become harder to come by. And so I think there may be places like the moon where there's this, what do I want to say, kind of an indentured servitude type economy would exist where if you can't have machines, then gross human labor becomes a commodity.
Right.
I think you may see situations where colonies may say, "Oh, okay, volunteer to work in our mines for a period of 5, 7, 10 years, and then we grant you corporate citizenship and the ability to live in our colony if you survive 10 years." And in places where mechanical power is really unfeasible because the heavy industry to support it and create it isn't there, then human labor built the pyramids. Certainly, human labor can do terrific things, but yeah, it's never going to be a pretty process.
Okay. Let's see. There was a question about from from Mara Doxbat. Okay, do you believe in free will? I'm not sure how that applies to our show today, but what do you think?
The problem of free will. That's a straight up philosophy question.
Yeah, it's a classic philosophy question. Yes.
I would say, as a scientist, yes, absolutely. I do. Free will kind of is a foundational assumption. It's one of the axioms of scientific method. Because if there's no free will, then there's no sense doing experiments. The outcomes are all predetermined. So, yes,
There's
short
no such
answer.
thing as discovery or so many things, right? So,
yeah. Discovery is always tricky. To say the first to do what, how much. So, anyway, but that's an interesting one. But thank you. Trying to tangle us up in the morass of philosophy.
Yeah.
Pekka is wanting to know, what do you think about the new quantum theory about time?
Oh, the time crystals and all of that.
I suppose.
I haven't gone down that particular rabbit hole very far. There are more shells on the beach than I have time to examine. Borrowing sloppily and greatly from Newton. Yeah, I haven't really got into that one yet. I'm very interested right now. I'm looking at finished reading The Search for Life on Mars, which is kind of a survey of the search for life on Mars from about 1960 through 2010, 2012, thereabouts. Didn't include Perseverance and some of the latest stuff. But very interesting. And I think I mentioned I'm reading No Shadow of Doubt about the 1919 eclipse and all the people and personalities involved in it. These things science is a human activity.
Mm-hmm.
And so you can't talk about science unless you talk about the behavior of people who do science and their choices and the odd things that happen in their lives that affect discoveries, speed them up, slow them down. And so many things like that. We talk about Kepler's search for the elliptical orbit and how he found it and rejected it several times. And he wasn't ready to see it. He wasn't ready to hear it. He wasn't ready to accept it.
I see.
But this idea that we can only see things when we're ready to see them. I often talk about bring more knowledge to the eyepiece. You will take more away. So you learn about what you're going to be seeing before you go observing. And you will take a lot more away from the experience. So I don't know if that's a good answer or a bad one, but there we go.
I think it'll suffice.
So, you guys, which one is your most interesting question?
Well, I have.
What's the most interesting question, do you think, Barth, today?
I very much like the one from Jafar early on, where we're talking about different neutron particles and things like that. Mike Wiesner's Phase of Venus. is the second one that I liked because phases of Venus. This is, many people don't know this. This is the observation that Galileo used to prove that the sun must be at the center of the solar system. And you can observe the phases of Venus, and you can do this activity with a very, very modest 50 millimeter toy telescope. Um, and you can watch these phases and document them. And you can follow Galileo and say, yes, I understand now that this could only happen with the sun in the center of our universe, the pattern of changes and movement. So I find that one very profound. The third one that I really like was from Lubo, our friend in China, and that's the one on the modified gravitation. Uh, the search for dark matter seems to me to be making a lot of parallels as the search for the ether. And the ether was the mysterious substance through which light waves waved. And we spent a century or more looking for this and talking about it and saying, oh, it must be this, it must be that, it must have these properties. And finally, someone came along and said, no, I have a seminal experiment here that shows it's not there. Or if it affects nothing, so it doesn't matter if it's there or not. That was actually one of the arguments that were made. Well, perhaps the ether is all these things you say, so thin, so tenuous that we cannot measure it, and we cannot measure it interacting with our universe. And someone very cogently pointed out, if you cannot determine that it interacts with anything in the universe, it isn't of our universe. Being part of our universe means you can interact in some way. And dark matter, right. They say, this goes back to, one of the Star Wars Obi-Wans. Oh, the planet is removed, but gravity's shadow remains. That's exactly the way we talk about dark matter. It's out there somewhere. It's interacting with things gravitationally. It's doing things to the way galaxies rotate. Well, what if, in fact, it's not there? And when you get that much mass, galactic mass is involved, gravitational physics changes under the stress. And so that's why gravities don't rotate the way solar systems rotate. It's just an effect of the mass. And so the modified dynamics, to me, cuts right to the heart of one of the most fundamental mysteries in science today. And so I like that. I like that ideas that reach and grasp and struggle with things unseen and unknown. So we'll have 3 books. One will go to Jafar, one to Mike Wiesner, one to Lubo, and I'll leave it to you guys to contact us. And Scott will post up an email. You can contact me at astronomyforeducators@gmail.com.
We'll just use that. Yep. I'll put it into the...
Yeah, give us the information so we can...
And then Dr. Barth will send that information over to us, and we'll make sure that those books find their way to you. So
yes, and you need to tell us how you would like them signed. And I have promised to sign as you wish within reason.
Yes, the caveat.
And Paul is giggling right now. So what's reasonable for me, being fairly stodgy and old-fashioned, is probably not everything that's reasonable for Paul. But
I have a funny story about having people sign things. Okay, sometime one of these days, I'll drag out my Sky Atlas 2000. It's a star map. It's large. It's a paper, bound, but it's a paper star map. And as I went to star parties over the decades, I would have people sign it. And some people who signed it have included, like Clyde Tombaugh, who discovered Pluto. Okay. Buzz Aldrin signed it. I've had people that flew in space. I've had people that were just average amateur astronomers that were just hanging out with me. They got to sign on the same page as some great discoverers and stuff. So I didn't like keep those signatures like away from other signatures. I just wanted to
No.
have everybody sign it, which is really funny and really it's great. But the funniest story I have about anybody signing my star chart was from a guy named Tom Cave. Now, if those that have been in amateur astronomy for a long time will remember that there was a once upon a time a company called Cave Optical. Okay,
Oh, yes.
they were the Celestron, Meade, Explorer Scientific of their day.
They were.
Very popular brand, and so. But Tom Cave eventually retired, and and passes on the baton. So people that used to work for Tom Cave actually worked at Meade Instruments. A lot of them. I never worked for Tom Cave, but I got to meet some of the older engineers and people, and they even remembered companies from before that time. So for me to meet Tom Cave was a big deal to me. Here I was going to meet a former titan of the telescope manufacturing industry, and so I asked. Somebody said, "Hey Scott, that's Tom Cave over there. You should get him to sign your star chart." And I said, "Great." And so I walk up to Tom Cave, and I said, "Mr. Cave, would you please sign my star chart?" He didn't have a very good look on his face. He was looking at me with kind of like some disdain. I don't know what or why, that he didn't, meet me with a nice big smile, but he didn't. And I said, and I thought maybe I somehow offended him or something. I said, "Gosh, I'm sorry." I said, "I just." To me, you're like one of the heroes out there, and I would love for you to sign my star chart. And I said, here's my star chart. Here's a pen. I'll just go away, and you can write anything that you want to. I said, give me something to remember you by. So the star chart was open, okay? And I go away for like, I don't know, 15, 20 minutes. And I come back. Tom Cave's gone, okay? And the star chart's closed, and the pen's on top of it. And I go, wow, okay, he signed it. I wonder what he wrote. And so I'm thumbing through the pages, and I finally get to this one page, and there's Tom Cave's signature, and it says, "Go to hell, Tom Cave." And that's the funniest story I have. It's probably the best story I have about anybody signing anything for me. So, I guess he didn't want to sign my star chart, but he did anyway.
I guess not. I guess not.
I guess
Go
not.
to hell,
That
Tom.
was funny. That was funny. I was laughing so hard. Now, this is at the Astronomical League convention, I think in Des Moines, Iowa. I'm laughing so hard that I actually fall on the ground laughing and cannot stop laughing. Crazy. Totally unexpected. It was sincere. Airlock says it was sincere.
That's hilarious.
So, anyhow, I don't imagine you'll be writing that for anybody.
No, I don't think so. I did have
Not even me?
my best signature story was Clyde Tombaugh, and I went to I forget, it was somewhere, it may have been Griffith Observatory, and they had Clyde out to speak, and we go
Yep.
out afterwards and look in some 10 and 12-inch scopes and see Pluto.
Sure.
And afterwards, he was sitting, and people were coming up, and I said, "Mr. Tombaugh, I brought a copy of a book by a mutual friend of ours. I was hoping you might sign for me." And he looked up and he said, "Kid," I was about 26 at the time. He says, "Kid,
Yeah.
who the hell would you know that I know?" And I held up my copy of the Principia and I said, "Isaac Newton." And he laughed. He says, "Yeah, okay, I like Ike. I'll sign." And he
sign that.
signed my name. And so there you go. There's
Yeah.
my funny.
Well, that's great.
All right. Well, next time when we come back, Scott, episode
Okay.
51, we will start a new
The real
journey at
51, right? Okay.
51, and we're going to indeed have a program on magnetars. So that will be exciting, and I'll look forward. Our winners from today, contact me and send me your shipping information so we can. Please understand that we don't have the books in hand right now. We're waiting for our copies from Springer. So I go jumping with glee down to the mailbox every day. Oh, not today,
Oh, not there.
but soon.
That's what happens when I take my
soon.
lottery ticket to the gas station.
There you go. That's exactly right. So that's great, and we will be seeing you next week.
Sounds good. Sounds great. Thanks, everybody. Thanks for all the great questions.
Yes.
And tomorrow night, we will have the 98th Global Star Party.
That's awesome.
So we're looking forward to that. It's about exploration and awakening, So
Yes.
I was inspired by looking at some of videos of astronauts describing the overview effect that was so coined, I guess, in 1987. And a book has been made about it, and a documentary has been made about it. But it is the change that happened to astronauts as they viewed the Earth rising over the horizon or seeing Earth from space. I contend that astronomers too have an overview effect, especially for like events like a total eclipse of the sun.
Yes.
There are things that happen where, and you can see it happen when people kind of go over this tipping point and they realize, sometimes it hits them quite strongly, that they are in fact on a planet hurtling through space. So this astronauts describe Earth as like a natural spaceship. Okay, with all the things that keep us alive and protected. We have our own force field, all of that. So it's just it is kind of amazing to think about. And but this is the topic and the theme for the 98th Global Star Party. And then we're going to take a couple of weeks off before we come back to the 99th Global Star Party, which I think happens July 12th. And then the week after that, we will have the 100th Global Star Party. The reason that we're taking this time off is that I'm going to California, and we have an event up at Mount Wilson, which I will be broadcasting some elements of that live. It happens to be the family reunion of George Ellery Hale, and it's being celebrated by Caltech and Mount Wilson Observatory. So I think it's the first, I don't know if it's the only family reunion that the Hale family has had. Maybe they've had some in the past, but it's been a very long time. Generations have passed since that time. And so it may be the one and only time when so much family actually gets together. Dr. Wendy Friedman is going to be giving a talk during that time, and other people from Caltech will be there. So it should be pretty interesting. And that happens coming up at the end of this month on the weekend. So I'll try to update people on times and all of that as this gets underway. But it will be historic. So that's all I have for right now. And we hope that you're with us tomorrow on Global Star Party.
Sounds good.
Okay.
See you guys next
I
week.
think that's a wrap.
Bye.